A telescope in South Africa picks up something unexpected, a burst of radio frequency, not from Earth, not from our solar system, from an object that shouldn't be here at all. The object is 3I Atlas, an interstellar comet, a visitor from another star system hurtling through our cosmic neighborhood at impossible speeds. And now it's speaking. Or at least that's what the headlines want you to believe. What would you do if you were the first person to see this signal? For the first time in human history, we've chemically analyzed material from outside our solar system, not through distant spectroscopy of exoplanet atmospheres, not through meteorite fragments that might have interstellar origins, actual, confirmed, real-time observation of an object born around another star. And what we found changes everything we thought about how common water really is. Let me take you back to the moment everything changed. It's 2025. The MeerKAT radio telescope array, nestled in the Karoo Desert, is sweeping the southern sky. 64 dishes, working in perfect synchronization, listening to the whispers of the cosmos. They're trained on 3I Atlas, the third confirmed interstellar object ever detected. Scientists expect nothing unusual, just another observation session. Routine data collection. Then the spectrum lights up. A distinctive absorption line appears at 1820 megahertz, the hydroxyl radical frequency, the fingerprint of water being torn apart by solar radiation. It's unmistakable. It's real. And it's coming from an object that traveled light years to reach our doorstep. The scientists stare at their screens. They run diagnostics. They check for interference. They verify the calibration. Everything checks out. 3I Atlas isn't just reflecting sunlight. It's actively degassing, breaking down, revealing its chemical secrets as it races past our planet. This is the first time we've ever detected radio signatures from an interstellar visitor. The first time we've chemically analyzed something born around another star. Think about that. An object older than human civilization, forged in the gravity well of a distant stellar system, is now close enough to study, close enough to understand. Let me put this in perspective. Oumuamua gave us nothing. It was too small, too fast, too unexpected. By the time we realized what it was, the object had already passed perihelion and was racing away. We got optical observations, trajectory data, brightness measurements, but no chemistry, no composition, no direct evidence of what it was made from. 2I Borisov was better. We confirmed it was a comet through visual observations, detected a coma, measured dust production. But radio spectroscopy, that requires the object to be close enough, active enough, and observed at exactly the right moment with the right instruments. 3I Atlas hit that perfect window, and MeerKAT was ready. This is the first time we've obtained direct chemical composition data from an interstellar visitor. The first time we've proven, not inferred, that water ice exists in objects from other stellar systems. That's not incremental progress. That's a categorical breakthrough. The detection happens at dawn, South African time. The operators on shift barely comprehend what they're seeing. They call senior researchers, wake them from sleep. Within an hour, the data is being analyzed by teams across 3 continents. By noon, preliminary reports are circulating among the astronomical community. By evening, the news breaks publicly, and that's when everything spirals. Comment what you think is happening, even one word. Let's talk about what MeerKAT actually detected. The hydroxyl radical. 2 atoms bonded together. 1 oxygen, 1 hydrogen. Chemically represented as OH. It doesn't exist naturally in deep space for long. It's unstable, reactive. It forms when ultraviolet light from our star strikes water ice embedded in the comet's surface. The photons break apart H2O molecules. What remains is OH, drifting away from the nucleus in a thin, expanding cloud. This cloud absorbs specific radio frequencies, 1820 megahertz to be precise. It's like a cosmic barcode. When MeerKAT's dishes captured background radio emissions passing through 3I Atlas's coma, the hydroxyl molecules left their signature, dark lines in an otherwise continuous spectrum. Absorption features that reveal composition, density, and activity level. This is what astronomers call a radio detection in cometary science. It's not a transmission, not a broadcast. It's the passive chemical fingerprint of outgassing. Natural, predictable, beautiful in its simplicity. The process works like this. The comet nucleus, probably just a few kilometers across, contains frozen water mixed with dust and organic compounds. As it approaches our star, temperatures rise. The surface begins to warm. At negative 100 degrees Celsius, water ice starts to sublimate. It doesn't melt. It transforms directly from solid to gas. This vapor escapes through cracks in the crust, forming an atmosphere around the nucleus. A coma. Solar radiation hits this coma. Ultraviolet photons carry enough energy to break molecular bonds. Water molecules split. Some become hydrogen and oxygen atoms. Others become OH radicals and hydrogen atoms. The hydroxyl radicals are particularly interesting because they're excellent radio absorbers. They exist in specific quantum states. When radio waves at exactly 1820 megahertz pass through, the OH molecules absorb that energy. They transition to higher quantum states. The radio wave emerges weaker at that specific frequency. MeerKAT detected that weakening, that precise absorption signature, its spectroscopy at its finest. And it works the same way whether you're studying a comet from our solar system or one from another star. But here's where it gets complicated. The word radio signal hit the news cycle, and the public mind went exactly where you'd expect. Radio signal equals transmission. Transmission equals intelligence. Intelligence equals extraterrestrial technology. Within hours, social media erupted. Forums buzzed with speculation. YouTube thumbnails screamed about alien spacecraft. The narrative took on a life of its own. Science had detected something extraordinary. The internet decided it had detected something impossible. The confusion is understandable. For decades, radio telescopes have been associated with SETI, the search for extraterrestrial intelligence. Projects like SETI at home captured public imagination. The idea that radio telescopes are primarily listening for alien broadcasts became embedded in popular culture. So when news breaks about a radio detection from an interstellar object, the mental connection happens instantly, unconsciously. Scientists try to clarify. Press releases emphasize absorption lines, natural chemistry, expected cometary behavior. But nuance doesn't survive the translation. From technical papers to headlines to social media posts, each retelling strips away context, amplifies excitement, distorts meaning. This pattern repeats throughout astronomy's history. 1977, the wow signal. 72 seconds of radio that never repeated. 2007, fast radio bursts from distant galaxies. Initially mysterious, now understood as magnetar flares. 1967, pulsars with their precise timing, briefly nicknamed LGM, one little green men, one until we found dozens more. The cycle is always the same. Mysterious detection, public excitement, media amplification, scientific investigation, natural explanation. But that emotional arc from wonder to understanding never diminishes. And the gap between technical language and public interpretation creates fertile ground for extraordinary claims. When astronomers say radio emission from a comet, they mean passive spectroscopic signatures. When the public hears radio signal, they think active transmission. That linguistic gap explains everything that happened next. So what do these hydroxyl molecules actually tell us? Water. The comet contains water, ice, probably substantial amounts of it locked beneath a dark, carbon-rich crust. As 3I Atlas approached our star, solar heating reached deep enough to sublimate that ice. Solid became gas without passing through liquid. The vapor escaped through cracks and vents, carrying dust particles with it. Sunlight hit the escaping H2O molecules and shattered them. OH radicals formed. MeerKAT detected the result. This is textbook cometary behavior. Every icy body that enters the inner solar system goes through this process. Halley's Comet, Hale-Bopp, Neowise. They all produce hydroxyl signatures when observed at the right wavelengths. The chemistry is identical. The physics is identical. The only difference? 3. I-Atlas didn't form here. The water in this object condensed from a protoplanetary disk orbiting a star we cannot name. It witnessed planetary formation around a stellar system we may never visit. It survived ejection, gravitational perturbation, interstellar void, radiation bombardment, and now, billions of miles from home, it's showing us that the same chemical processes operate everywhere. It's just water. Frozen, ancient, from another sun. Think about what that means. This water froze perhaps 4 billion years ago, maybe more, around a star that could be anywhere within a few hundred light years. The comet formed in a debris disk, accreting ice and dust, grew large enough to survive. Then something happened. A close encounter with a planet, a stellar flyby, gravitational chaos. The comet was flung outward, escaped its birth system, entered interstellar space, traveling at tens of kilometers per second. For millions of years, it drifted. The temperature dropped to near absolute zero. Cosmic rays pelted its surface. Interstellar dust eroded its outer layers. But the ice remained, protected by insulating crust, waiting. Then our star's gravity caught it, drew it inward, accelerated it to nearly 50 kilometers per second. As it crossed the orbit of Jupiter, solar heating began. The long dormancy ended. Ice that had been frozen since before Earth existed started to wake up, started to evaporate, started to reveal its secrets to anyone capable of listening. Water is universal. Ice formation is universal. Cometary activity is universal. 3I Atlas is behaving exactly like a comet should, which, paradoxically, makes it even more fascinating. Not because it's alien technology, because it's proof that nature follows the same rules across light years of space. Simple chemistry, vast implications. A equals natural phenomenon, B equals unknown process, C equals something entirely new. Comment A, B, or C, no wrong answers. But not everyone agrees with the natural explanation. Avi Loeb, Harvard astrophysicist, former chair of the astronomy department, author, public intellectual. He's been arguing since 2017 that Oumuamua, the first interstellar object, might be artificial. A light sail, a probe, technology from another civilization. His reasoning? Its unusual acceleration, its elongated shape, its high reflectivity. The mainstream astrophysics community pushed back hard. Natural explanations exist. Outgassing asymmetry, fractal structure, nitrogen ice. The exotic hypothesis requires extraordinary evidence, and extraordinary evidence hasn't materialized. Now, with 3I Atlas emitting radio signatures, Loeb and others are asking new questions. Why this particular frequency? Why such strong hydroxyl production? Could the chemistry be engineered rather than natural? The scientific community's response has been swift and decisive. Radio spectroscopy of comets is not new. We've detected OH emissions from dozens of solar system comets. The frequencies match perfectly. The production rates align with calculated ice sublimation. There's no anomaly here, no deviation from expected physics, no need for exotic explanations. Planetary scientist Karen Meach, who led studies of Oumuamua, emphasized this point in recent interviews. We need to distinguish between what's unusual and what's impossible. 3. I-Atlas is unusual because it's interstellar. Its chemistry is completely normal. Other researchers have been equally direct. Cometary scientist Michael Kelly from the University of Maryland stated that the hydroxyl detection is exactly what they'd expect from any icy comet at this distance from our star. The production rate, the spatial distribution, the spectral characteristics, everything matches theoretical models developed from decades of observing solar system comets. The standard is clear. Extraordinary claims require extraordinary evidence. A hydroxyl detection from an icy comet is not extraordinary evidence. It's confirmation of the mundane. And in science, the mundane is often exactly what we need. But why does the artificial hypothesis persist? Why does it capture attention despite lack of supporting evidence? Part of it is human nature. We're pattern-seeking creatures. We evolved to detect intention and agency. A rustling bush might be wind, or it might be a predator. Our ancestors who assumed agency and ran survived more often than those who assumed random chance and stayed. That bias remains hardwired. We see faces in clouds, hear messages in static, find meaning in coincidence. Part of it is hope, the desire to not be alone, to believe that intelligence exists elsewhere. That contact is possible, that the universe contains others who think and wonder and create. That hope is beautiful, understandable, very human. And part of it is the nature of scientific discourse. Science thrives on debate, on competing hypotheses, on challenging assumptions. Loeb's willingness to propose exotic explanations, even when unlikely, serves a function. It forces the community to examine evidence carefully, to articulate why natural explanations are sufficient, to test the boundaries of what we know. This is a victory for observation over imagination. For decades, we've wondered what interstellar comets would look like, how they'd behave, whether their chemistry would match our solar systems. Now we know. The answer is yes. Comets are comets. Water is water. The laws of thermodynamics don't care about stellar zip codes. But the path from detection to understanding was complicated by public expectations, by decades of science fiction, by the very human desire to believe we're on the verge of contact. When you've grown up watching Close Encounters and Contact and Arrival, your brain is primed to interpret ambiguous signals as meaningful, as intentional, as communication. This is the challenge of modern science communication. Data exists independently of interpretation, but interpretation shapes public understanding, and public understanding drives funding, policy, and cultural narrative. When a hydroxyl detection becomes an alien signal in the span of one news cycle, scientists face an uphill battle. They must correct misinformation while maintaining public interest, explain complexity without condescension, defend rigor without seeming closed-minded. 3i Atlas offers a masterclass in this balance. The detection is real. The excitement is justified. The interpretation matters enormously. And getting that interpretation right requires patience, expertise, and a willingness to embrace the less sensational truth. Does this change how you see our place in the universe? But here's what really gets me. We're living through a moment of cosmic discovery that previous generations could only dream about. 30 years ago, we didn't know if planets existed around other stars. We had theories, hopes, no proof. Now we've confirmed over 5,000 exoplanets. We've detected atmospheres, measured compositions, found water vapor, organic molecules, phosphine on Venus, methane on Mars, hydroxyl radicals on interstellar comets. We're building an inventory of cosmic chemistry, slowly, methodically, learning what's common and what's rare, what's universal and what's unique to our little corner of space. And every single data point matters. Every spectrum, every absorption line, every confirmed detection. 3i Atlas is one data point, but it's a profound one. It tells us that comets from other stellar systems carry water, that they outgas when heated, that we can study them with our existing instruments, that interstellar visitors aren't exotic mysteries forever beyond our reach. They're analyzable, understandable, part of the same physical universe we inhabit. This is what scientific progress actually looks like. Not dramatic revelations, not paradigm-shattering discoveries every week, incremental understanding, careful measurement, hypothesis testing, the accumulation of small truths that eventually form a larger picture. Stop for a moment. Think about what this means. An object older than most stars in our night sky just told us its secrets in radio waves, in a language we learn to speak. So what happens next with 3i Atlas? As the comet moves away from our star, solar heating will decrease. Outgassing will slow. The hydroxyl cloud will dissipate. Eventually, 3i Atlas will return to the cold silence of deep space, carrying its water ice intact once more. Our window for observation is closing. Every day it gets fainter, more distant, harder to study. But we're not done yet. Other telescopes are watching. ALMA, the Atacama Large Millimeter Array, can detect carbon monoxide and other molecules. The James Webb Space Telescope, with its infrared capabilities, might catch thermal signatures or dust composition. Ground-based observatories are tracking its trajectory, refining orbital calculations, searching for any additional anomalies. We're looking for carbon dioxide, for ammonia, for methanol, for formaldehyde, for hydrogen cyanide. Each molecule tells part of the story where the comet formed, what temperatures it experienced, what stellar environment created it. These are questions we've never been able to ask before, and now we can. The isotopic ratios could tell us even more. If deuterium levels are unusually high, it suggests formation in an extremely cold environment. Perhaps the outer disk of a red dwarf system where temperatures barely exceed 10 Kelvin. If carbon-13 ratios match our solar systems, it implies similar stellar metallicity, similar age, similar formation conditions. Some researchers are already speculating. The water chemistry hints at formation around a G-type star, like our own. But we need more data. If ALMA detects strong carbon monoxide and weak carbon dioxide, that would suggest birth in a cold outer disk region. If the ratio flips, high CO2, low CO, we might be looking at formation closer to its parent star, perhaps around a K-class star, slightly cooler than our own, where volatile retention patterns differ. Every molecule is a puzzle piece. Every isotopic measurement narrows the possibilities. We might never know exactly which star system ejected 3I Atlas, but we can constrain the type of system, the temperature range, the chemical environment. That's something previous generations of astronomers could never have imagined doing. And there's the question of future visitors. 3I Atlas is the third confirmed interstellar object. Oumuamua was first. 2I Borisov was second. Statistical models suggest dozens pass through our solar system every year. We just haven't spotted them. But survey telescopes are getting better. The Vera Rubin Observatory will begin operation soon, scanning the entire visible sky every few nights. We'll find more interstellar comets, more asteroids, more opportunities to study material from other stellar systems. Each one will teach us something new. Each one will refine our understanding. Let me leave you with this thought. We're standing at the edge of a new era, not because we found aliens, because we found the universe is more accessible than we thought. The galaxy is messy. Stars eject material. Comets escape their home systems. And occasionally, one of those wanderers passes close enough for us to study. 3I Atlas traveled for millions of years, crossed light years of empty space, survived cosmic rays and interstellar dust. And when it finally entered our solar system, it behaved exactly as physics predicted. It heated up, it outgassed, it revealed its composition, it showed us that water exists elsewhere, that comets are universal, that the cosmos operates on principles we can understand. This isn't the story some people wanted. It's not alien technology or evidence of extraterrestrial intelligence. It's something better. It's confirmation that our science works, that our models are sound, that the universe, despite its vastness and strangeness, follows comprehensible rules. The search for extraterrestrial intelligence continues. The hope for contact remains alive. But it requires patience, rigor, the willingness to do the hard work of eliminating natural explanations before embracing extraordinary ones. The unknown is not a void, it is an invitation. 3I Atlas will fade into the darkness soon, but the data remains. The questions multiply, and more visitors are coming. The Vera Rubin Observatory will find them. JWST will analyze them. We'll build a catalog of interstellar chemistry, object by object, molecule by molecule. So here's what I want from you. Not just a comment, a prediction. What's the one molecule you think we'll find in the next interstellar comet that will surprise everyone? Carbon chains? Amino acids? Something we haven't even considered? Drop your answer below. Hit subscribe and turn on notifications so you don't miss when the next data drops from Webb and Alma. And if you know someone who thinks space science is boring, share this with them because this is just the beginning. What do you think we'll discover next?